Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on the 26th of June, 2025 T, 17 hours, 41 minutes and 7 seconds, .0000Z. This paper, published just yesterday, introduces a new framework that boosts segmentation accuracy by nearly 50% over previous methods. The paper is titled MADrive, Memory-Augmented Driving Scene Modeling, and this approach is a big step towards creating truly robust simulations for testing self-driving cars. The authors achieved this by building a massive new dataset of car videos and using it to replace partially seen vehicles with complete, relit 3D models. This first figure really shows the power of this approach. We start with a training frame where we only see the side of a car making a turn. The model then accurately reconstructs a future moment in time, looking nearly identical to the real video. But the most impressive part is the final panel, which shows a completely new, alternative scenario. Here, the car is rendered from a viewpoint that never existed in the original data. This ability, called novel view synthesis, is key for creating diverse and critical test cases for self-driving AI. So, how does the system actually accomplish this? This next diagram lays out the entire MADrive pipeline. First, on the left, it takes the partially seen car and uses a retrieval module to find the closest match in its massive database. Then, the system uses videos of that retrieved car to build a complete 3D model. It does this using Gaussian splats, which are basically thousands of tiny, colored, semi-transparent dots that create a photorealistic object. It also estimates the scene's lighting with an environmental map, allowing it to relight the new car so it fits perfectly. Finally, it composites this new, complete car back into the scene. Building on that pipeline, the success of this whole system really hinges on that massive memory bank of cars. And these charts give us a look inside that database, which the authors call the MADcars dataset. On the left, we see a good distribution of colors, with white, black, and dark blue being the most common. The middle chart shows that sedans and SUVs make up over 80% of the vehicles. Finally, the lighting conditions are mostly sunny or cloudy. This diversity is crucial. It's what allows the system to find a good match for almost any car it sees. And that diversity really pays off, which we can see in this direct comparison. This figure puts MADrive head-to-head against other methods like street Gaussians and auto-splat. The top row shows that all models can reconstruct the original training views just fine. But the bottom row, showing a future unseen moment, is where the difference is stark. The ground truth on the far left is the actual video. You can see the other models produce a blurry, fragmented car. They just fall apart. MADrive, however, creates a solid, realistic vehicle, looking almost identical to reality. And those visual improvements are backed up by the numbers. This table quantifies the performance on tracking and segmentation. We see MADrive leading across most key metrics. For instance, both multiple object tracking accuracy, which is how well it tracks all cars, and the IDF1 score, which measures if it keeps the right identity on a car, are significantly higher. But the biggest leap is in segmentation intersection over union, a measure of shape accuracy. Here, the score jumps from 0.556 to 0.822. This huge improvement confirms that MADrive's reconstructed cars are measurably more accurate. Beyond those numbers, this next figure really drives the point home visually. We're looking at a qualitative comparison on the Kitty 360 dataset. The top row, labeled GT, is the ground truth, the real car. Below, you see what different models reconstruct. When you look at the rotated views, the other methods, like UrbanCAD and DiffSplat, produce distorted, almost melted-looking cars. But MADrive, especially when using its own MADcars dataset, creates a much more realistic and solid 3D model. This visual robustness is exactly what's needed for creating believable simulations. So what we see here is a really clever solution. Instead of trying to guess what the missing parts of a car look like, MADrive just looks it up. It pulls a complete photorealistic 3D model from its massive memory bank and seamlessly stitches it into the scene. This memory-augmented approach is what allows it to generate incredibly realistic and robust simulations, far beyond what previous methods could achieve. This is a big step forward for testing autonomous driving systems in all sorts of critical what-if scenarios. That's all for this week's AI Research Roundup. Thanks for tuning in.